Good morning. Welcome to Krishna's classroom. In the Riesz representation theorem, we explore the relationship between linear functionals and the measures. So, if what we have is the following: if you consider C01, let lambda be a non-negative, rather you can call it positive linear functional. Then there exists a finite positive oral measures mu on 0,1 such that lambda f equal to f d mu. Okay. Now f belongs to that means if lambda is a positive linear functional, then there exists a Borel measure on interval 0,1 such that the linear functional is represented by an integral of f in terms of the measure. So, this is the connection that links the lambda with mu. Of course, we have said C01 and can push the whole thing up to L1 space. Okay. Now, what we want to do is, because the converse of this result is obvious. Okay. One can easily show that mu is a positive Borel measure on 0,1. Then integral for a measurable or for a continuous function is measurable, obvious. Integral f d mu is well defined, and this defines a positive linear functional on C0. So, this connection is well established. Now, this relationship is now something that we want to explore. Okay. So, more or less, what more you can do? Suppose G is a bounded function on then you see that this defines a measure. So you see that, say, lambda tilde f integral g f is a measure, is a linear function. Or one can use this notation, lambda g, lambda sub g. Okay, but what you can do is this: if g is positive, then you see that this defines a positive linear. Now what you can do is the following. See that there exists a measure, moral measure. Nu on 0, 1 such that so you are connecting this with this one. This is another connection. So you see that it says you start taking bounded continuous functions on the interval 0, 1, which is non-negative, then you can always define these measures. Some connection that you have, but this is not something strange, because you know that you see what, look at this one. This is equal to, we are working on continuous functions, so on. So what you have is this integral see, you can write down this as integral now you see g d mu you can rework. Okay, what one does is this. Okay, if g is non-negative, then what happens? You look at this one, integral 0 to x g d mu, this is equal to greater than or equal. And in fact this is a monotonically increasing function. Okay, so this defines a monotonically increasing. Suppose you use this function and then take the derivative of that. So the derivative of this, suppose you call this h. H derivative, partial derivative, h derivative equal to g. Okay, so you can write this integral as can be written as h derivative t. F h derivative t. Okay, but what about this? Right? This you can write as integral 0 to 1 what would you get? F dh. Okay. Now this part is essentially E. That's how the measure comes. I mean, this is the classical result that you have. Okay, this corresponds to what you call the change of variables in the integral. Okay, so we shall come back to this later, but just leave this in your mind, and we shall now build the preliminaries. Now, what are the preliminaries that are required? In fact, the C01 is a linear space. For that linear space structure is there. But more than that, you see, what we require in our analysis is the topological structure that you have on it. So that in such a way that the measurable class of sets that you have contain all the open sets. So there is the fusion between the topology and or the smooth fusion between the topology and the measure. This relationship is as follows. So this is what you call the Borel sets. So you need to work on what is called the smallest sigma algebra that contains all open sets, so that there is the perfect what you call synchronization between or the harmony between the two structures, namely the topological structure and the measure. Okay. So what we need is this, and just this across. So the topological properties are relevant for our, certainly have to be highlighted because they would be coming every now and then with our analysis. So we have to have require all the open sets. Or we need require. See, this brings in lot of plenty of sets which are measurable. What happens is, if all the open sets are measurable, all the closed sets are measurable, then you see that if these are there in the sigma algebra, then you see that the countable union and countable intersection of such sets are again measurable. Okay, so you get a huge class of sets which are measurable. And one of the reasons that we require this, all the open sets are measurable, is the following. Suppose you talk about, take that interval 0, 1 and put it in a more general way. Suppose you have got x tau. Tau is a topology of that. Now we have a measure, the measurable class as contains all the open sets, or we choose the smallest sigma algebra which contains all this. So M is containing tau. That means all open sets. Okay, so this is called Borel measure. And then you define measure on this sigma algebra. Okay, so it's what you call the measure space, which you call a Borel measurable sets. Okay, so this in fact brings in quite a lot of sets, although ultimately you see that on the interval 0, 1 there are still non-measurable sets. So that is always there, but then that is something which you can ultimately ignore. Okay, and the Lebesgue measure that you get will be that for all subintervals of 0, 1, the measure will coincide with the length of the interval. Okay, so that is there. So this is a reasonable sigma algebra on which we can comfortably work on. Okay, I was trying to tell you why you need this. See, what happens is, suppose you take a function x to r or even complex value functions. Okay, now you see that f is continuous if for every open set R, f inverse of the open set O, f inverse of O x. What does this mean? This means f inverse of O is measurable. Because it's an open set. What further it means? It implies every continuous function is measurable. So it just assures us that all the continuous functions defined on x are now measurable functions. Therefore, you are assured that there is sufficiently large class of measurable function. Okay, so that's a very significant advantage that we derive by choosing a sigma algebra which contains the open sets. That's just a remark. Now we want, so let us see what topological properties we shall require, or just recall some of the topological properties that we will come across in our discussion when we move forward. Okay, right. So that's the general remarks I wanted to make. Now you see, there are in analysis always you will be working with, say, continuous functions and so on. That means there will be a topology on your space, and therefore what other things you do on that, it is better to take care of all the open sets, and that's what we are doing in this case. Okay, right. So what shall we do next? Yeah. So let us recall the topological. So we are given X with a topology. This topology is designated by tau, which contains a class of sets which are designated as open sets, having some properties like X belongs to this collection, then the empty set belongs to this collection, then you have what are called arbitrary union of open sets is open, and finite intersection of open sets is open. So these are the four important properties that tau should have. Okay. So X tau topology. Tau is the topology. Elements of tau are called open sets. So elements of tau so whatever discussion we make now will accept X with a tau. Okay. Now we define a few things, or just recall. I mean, these are all something that you already know. We just recall what are called closed sets. What are closed sets? A contained in X is closed if A complement open. That's the definition. So one of the things that you can observe is that X and are also closed sets because they are already open sets, so they are closed sets. Because you have empty set as X. So both X and phi are open, and therefore their complements are closed sets. The complement of phi is x, therefore x is closed. The complement of x is the empty set, therefore that is also. Now you see that one of the main important properties, that is the arbitrary intersection of closed sets you cannot say the same about arbitrary union. Okay, you recall in the definition of open sets, we said arbitrary union of open sets is open, finite intersection of open sets is open. So when you take the complementation, the whole thing turns around. You get arbitrary intersection of closed sets is closed and finite intersection of closed sets is closed. Now this is the consequence of that. This is because if you have A alpha closed, alpha is an index, then you see that means A alpha complement is open. So let us look at this one, arbitrary intersection. Intersection over alpha, A alpha. Now we take the complement of this. This is equal to union over alpha, A alpha complement. Now A alpha complement is open. Therefore, this is arbitrary union of open sets. Open. Okay. Therefore, its complement is intersection, arbitrary intersection of A alpha, and that is closed. That's something which we shall observe and we shall require having in mind. So the next property that we would like to recall now, if E is closed set, for any E closure exists. E closure is defined as the smallest closed set intersection of arbitrary intersection of closed sets. E is contained in A alpha. A alpha is closed. That means it is the intersection of all closed sets which contain E. Okay. E closure is the smallest closed set that contains E. So how do you get that? You get that by taking the arbitrary intersection of closed sets which contain, or you take all the closed sets which contain E, take their intersection, it is going to be closed, and that is the smallest closed set that contain. Okay. Okay, such. So the question that you ask is, does there exist an A alpha with such properties? Yes, because E is certainly contained X and X. So there is at least one closed set which contains. Okay. So now the next property is compactness. K compact if every open cover of K as a finite subcover. That means, suppose you take K to be contained in O alpha, O open. Therefore, this gives a open cover for K. Then there exists alpha 1, alpha n, or alpha k, such that K is contained in O alpha 1 union O alpha. That's what you obtain. Or that's the meaning of compactness. So every open cover is a finite subcover. Now, probably it is nice to look at this example. To take X to be equal to R. Then any interval, now you see that is compact. But now what happens is, you see, you take this one, 0, 1, this can be written as the union of with open neighborhoods of OX, where OX an open neighborhood of I'll take an open set containing X belonging to 0. Okay. Now, for example, you can write this one. Okay, let us take one and show that this is not complex. Claim so let us take this so 0 1 can be written as union over n 1 by n. Okay, so these are all open sets. So this provides an open cover for 0 1. But it has no finite subcode. That's very simple because suppose there exists a finite subcover, then 0 1 open interval 0 1 is contained in 1 by n1, 1 by n2, etc. 1 by union n I ranging from 1 to k of 0 1. Okay, but that is not possible because you see that nk, or you see that suppose you take the largest, suppose m is the largest of this n1, n2, etc. So you see that what you have is this. One. So if compact there exists. Okay, now we can choose like this also. We can choose this n1 and order them also such that this forms a cover. But this is impossible. This is not good. Because there exists some x belonging to 0 to 1 by nk, which belongs to 0 1 but not union I equal to 1 to k 1 by ni. Okay, so that's a contract. So there cannot exist any finite subcover which gives a cover for of the given cover. Okay. Now it's quite easy to show that this is the other one is compact. Okay. I don't want to deal with that. So now we talk about neighborhood. Neighborhood. A neighborhood of a point is any open set containing P. This is what you call a neighborhood. Now, this is not a very standard terminology because you use not only, so this gives an impression that all neighborhoods are open sets. Okay, but need not be. I mean, another terminology is that any subset of X which contains P and is contained in an open subset. So this is also sometimes it is defined as any subset of X containing P such that it contains an open set containing P. Okay, I'll make it clear. So you say that suppose B is a subset of X. Then B is a neighborhood of P if P belongs to B and there exists an open set O such that P belongs to O and O is contained. Now this is the other definition. I don't know, inadvertently I said something different earlier, I don't know, when I don't remember. So, this is the definition of neighborhood. So a neighborhood need not be in this what you call statement a open set, but generally you say an open set, any open set of X which contains P is taken as an open neighborhood. Sometimes it is called open neighborhood. X is said to be a Hausdorff space if given P belonging to X, Q belonging to X, P not equal to Q obviously, P not equal to Q, there exists open sets, there exists neighborhoods U of P and V of Q such that U intersection V is simple. Take two, so this is X, take 2 points, then you can find U, suppose this is P, this is Q, then V, such that the intersection between U and V is empty. So you can always separate any two distinct points in the space. That's what you call a Hausdorff. It's a nice separation criteria that often makes the analysis much simpler, or it conforms to, or in most of the topological spaces that you encounter in analysis has this property. So that's why it is specifically that. There are different types of separation properties that we have, and the general topological space you have a much more different type of separation, but this is something which we normally makes your life or what we probably need. Now the next one is X is said to be locally compact. Locally compact if X has, if every point has a neighborhood whose closure is common. Okay, so you see that on R is a, with the usual topology, is a locally compact Hausdorff space. That's an example. Or C or Rn is a locally compact Hausdorff space. Well, these are all the spaces that we will work. We'll have to work. One of the quick inferences is that every compact space is local. So many options. Remark. It's a direct application of the definition. So we have the famous Heine-Borel theorem. Now this is characterization of compact sets. It's a very important result. What the theorem says is this: K contained in Rn is compact if and only if K is closed and bound. That means a compact subset in Rn has the property that it is both closed and bounded. Conversely, every closed bounded subset of Rn is compact. Now you can easily see that this is not valid. Now remark, this characterization has limitations. In fact, it is not true in the infinite dimensional space. L2. What are L2? L2 are sequences xn. So it is actually fine. Now this is your L2. Now you take the unit ball, that means take such that sigma, or I will write it there. You take B 0 1, which is equal to neighborhood of 0, that is the unit ball centered at 0. This is the set of all sequences such that less than or equal to 1. This is the closure of the unit ball. Now this is closed. Bounded but not compact. Okay, so if you take the sequences En, okay, En lies on the surface of this ball. En is the one. En equal to delta n1 delta n2 etc. Now this is something that belongs to it's an element of it's a sequence in this, but you see that this sequence has no finite, no convergent subsequence. It's not a convergent sequence at all. Okay, because another way of characterizing this is that every convergent sequence or what you call every bounded sequence has a convergent subsequence, and that is non-validation. Okay, every bounded sequence is a convergent subsequence, and that is not true because this is a bounded sequence, but it has no convergent subsequence. Therefore, it's not bounded. So this is not okay. Now, one of the simple inferences is that Rn is locally compact of the space. Locally compact of space. In fact, one can prove that every metric space is a locally compact Hausdorff space. Okay, I think with this preliminary, let me conclude today, and then we'll take it up possibly tomorrow or day. Thank you very much.